Very good. So we should start right now. So our next speaker is Jonathan Scott. He will speak about interleavings and Gromov Hausdorff distance of categories. So please, Jonathan.
All right. Well, thanks very much to the organizers for giving me this chance to talk. Actually, here. There I am. Okay. So I'd like to say, I didn't put two and two together, but welcome to the second half of the Cleveland hour of this conversation. Nick is also here in Cleveland, at least that's where his university is. So what I'm going to be talking about today is about how trying to put some objects studied in topological data analysis into the greater perspective of category theory led us to realize that some common constructions are actually instances of things that are kind of more universal, and that could be that already exist in other settings, and sort of have a common generalization, which is pretty cool, and really one of the reasons why we well, with Peter Bubenik and Vin Da Silva, we started thinking about category theory in topological data analysis. Okay, so in particular, what the objects that we're in are these things called persistence modules that are like a distillation of parameterized topological data. One of the ways that you can compare persistence modules is through this idea of epsilon interleavings. And I guess what we did was we realized that this could be the existence of epsilon interleavings. It's really an extension problem. And by looking at it as an extension problem, that frees us from the sort of the classical definition of persistence modules, and to be able to define interleavings between any two functors, just as long as their domains are small categories. And if we allow ourselves to have, if these shape categories are in fact weighted categories, then we can get a distance out of it, a pseudometric, a logarithmic. Okay. And also, as I mentioned, we discovered that metrics from other areas of math turn out to be, well, just like interleaving distances. Okay. So what are these persistence modules? I realize this is not a TDA session, but so I won't go into too much detail, given only 20 minutes to talk. But essentially, if you look at a filtered complex, through various methods, you start with data, and you get yourself a filtered complex, and from this filtered complex, by taking homology or some other functor, you end up with a persistence module, which we're going to say so take homology, then you might end up with D being like graded vector spaces, or just finite dimensional vector spaces if you're only interested in a certain dimension. But what you have is a functor from this poset of real numbers into your category of interest. Number, you have an object, and you have morphisms. Whenever A is less than or equal to B, you have a map between the corresponding objects that is coherent with the poset structure in the real numbers. Okay. So to start thinking about how this could be categorical, or well, in the naive sense, you can think of translation on the real numbers as really being a natural transformation. Okay, so if x is less than or equal to y, then adding the same number to both sides gives you another inequality. The inequalities are your morphisms. And so we think of translations as being natural transformations from the identity functor to the translation functor. Okay. And that this is sort of the gateway to everything that we have done, really. Back in 2009, we had the original, or as far as I know, the original definition of epsilon interleavings. And that's where, so they're like isomorphisms where you've got to pay a cost, okay, by going back and forth between two objects. So what we have are if we have two persistence modules, then we can go back and forth by natural transformations. Let's say our persistence modules are F and G. You can go back and forth, but at the cost of having to translate. Okay, so if you can do it without translating, then you've just got a morphism of functors. So so going across one way, that's fine. You can also oh no, I'll do that later. Yeah, so if you go across and back again, then you end up like 2 epsilon units further down from where you started. Okay, so it's almost like there's a flow in between your two copies of the real numbers. Okay, so for an example, if you just have a persistence module, this would be like a characteristic persistence module for a subset where the subset of real numbers is an interval. So essentially, you've got a one-dimensional vector space for each point in the interval, just as the trivial vector space outside of the interval. You can have the identity transformation. You do have the identity transformation, okay? And, well, if the interval, what do I want to say here? Yeah, so if the interval is less than 2 epsilon, then you can start before the end, the interval starts, go across and back again to the 0, and you end up back where your characteristics persistence module is 0. So that means that these characteristic persistence modules for finite intervals can be epsilon interleaved with a 0 module for a given, okay, like the down to or up to, no, down to like half the length of, okay, all right. So here's a better picture of this. Of your 2 copies of the real numbers as being the two shores of a river, the 2 riverbanks of a river, and the river is in the positive direction at a rate of epsilon, whatever that means. Okay, and so so we cook up this diagram category, a small category in which, so we have the 2 copies of the real numbers. Those are, and that's all the objects we have, but we throw in morphisms corresponding to being able to cross the river, but at a cost of adding epsilon in either direction. Okay, and this means also, like, if you want, you know, you can also cross the river at a slower rate. You can go across and then up, no problem. Okay, this category we'll call, which we call I epsilon, I for interleaver. This is the category that describes epsilon interleavings in the sense that, yes, if you have 2 functors, two persistence, they can be epsilon interleaved if and only if you can extend just the sum of the 2 modules to this larger category. So you can fill in these morphisms. Okay, and then it's just a matter of chasing on definitions to see that this is precisely what an epsilon interleave, or this is completely equivalent to the classical notion of epsilon interleaving. And then and then we end up getting a metric from this by saying, okay, well, what's the smallest epsilon, or we take themum over all epsilon for which we can use extensions. And once we have this picture, then we see we can once we just have a simple diagram like this, we can start going around with what the nodes of the diagram are, and we say, well, this is a generalized interleaving. So here's our new setup. All right, let's say that we have any two functors, f and g, the same target category, C, but potentially different categories as a domain. We want them to be small. Typically, they'd be like a PO set or something, but they don't need to be. And what we say, there's an I interleaving between f and g, extend the two functors over I. Okay, where I isn't any old category, but you want to have these embeddings of your small categories of P and Q in I. So it might be something as simple as just the co P and Q, in which case an I interleaving wouldn't be very interesting. Everything is I interleaved for that embedding. Okay, but if you look at all possible interleavings, then you start getting somewhere. In particular, here's where here's where we see that sort of relations in other settings of mathematics are just like interleavings. And when we look at them in this extension problem point of view. So a discrete dynamical system, and what is on this page is basically the sum total of my knowledge of discrete dynamical systems, okay? So it's a total space X along with a self map. As you iterate it, you have a system evolving, okay? And so since you have all these iterations of the map for every natural number, we can think of this as just being a functor from the one point that has one morphism for each natural number into topological spaces where the image of your one point is your space X, and the generating morphism gets sent to your continuous self map. Okay, so we're already discrete dynamical systems as being like persistence modules. Okay, if you have two dynamical systems, well, they're said to be shifted with lag L. If going back if you've got continuous functions back and forth between X and Y, they're going across and back. So when you compose them, you don't get the identity, but it costs you this L iterations of your continuous map in either direction. And already this is when I say it like that, it sounds like it's some kind of interleaving thing. Of course, it came around earlier than interleavings, but in any case, it is an interleaving because you can construct this interleaver category where X and Y are they're going to be sent to your spaces of interest. Phi gets sent to one self map, psi gets sent to another self map, and going across and back, you just sort of declare that costs L iterations of the two non-identity self maps on X and Y. And so you get that two dynamic systems are shifted of lag L, if and only if the two functions corresponding to your dynamical systems extend over this larger category. Okay, so interleavings have been spotted in other categories, which is fun. Okay. Now, I haven't said anything. We'd like to say that, like here, we want to give each iteration of phi some sort of weight. So we want to be able to measure, like, you know, okay, so you can do it with lag 10. Can you do it with lag 9? I don't know. So we need to start measuring. We'd like to make this into some sort of a distance. Okay, some sort of a metric. Okay. And to this end, we introduce weighted categories. This is just where for every arrow in your category, you assign it a non-negative number that plays well with respect to composition of arrows. And then you just, between any 2 points and objects in your category, you just take the infimum of the weights, the cumulative weights of all the arrows from P to Q, and this gives you a Lavier metric space. Okay, you may have infinite distance, right? If there are no arrows from P to Q, that thing. And you could have zero distance between distinct objects, that kind of thing. But you get some kind of a metric. Okay. So now at this point we realized. So we want to be able to assign. You know, let's say you have two functors that are interleaved by some category. And you know, and everything is weighted here. We want to give a value to the leaving that would correspond to epsilon. Okay. So to do this, we realized that, well, okay, basically we now have ourselves a Gromov Hausdorff distance on the category of all small weighted categories. Oh, and maybe I'm getting ahead of myself a little bit here. If you have, so now we have this interleaver category I that's weighted, subcategory in Q, and you can define the Hausdorff distance between P and Q as if they were just two subsets of space. Okay, it's exactly the same definition. Details may differ a bit, but and then what you do is for each interleaving that you have, what do I want to say here? Oh yeah, no. Okay. All right. So this gives us we then consider this category of weighted embeddings. The objects are just these pairwise embeddings of your two categories inside the any larger category with the obvious morphisms. Okay. And there is a larger story in which these weighted embeddings, like the Hom categories in a two category, and that is kind of fun. And then you just define you can define a Gromov Hausdorff distance between two arbitrary weighted categories by taking the infimum of all of, so you look at everywhere where P and Q are embedded in the same category, you look at their distance in that category, and then you just take the infimum over all such embeddings. And then to get back to how to tell the distance between functors, well, you look at the infimum of all the possible distances P and Q, where now instead of looking at all the different embedding categories, you just look at the ones over which you can extend F and G. Okay, so you're taking a smaller collection. And then this allows us to well, have a pseudo metric on the category of all functors with small weighted domain. Okay, I think that is, yeah, that's it. So So it's a talk where instead of a theorem at the very end, it's well, it's basically a definition. But I'm hoping that this will be perhaps seen as a warm-up for Peter's talk coming up later this evening. Thanks very much.